And so what we're going to be talking about is what's called optimization problems, max-min problems. They're word problems. Overall, the actual concept is pretty simple, but they're word problems. And I know from experience of doing this for who knows how many years that word problems tend to cause us a little more trouble. So I will tell you that these do tend to give you some trouble. They tend to be more about the setup of the problem giving you trouble and less about the actual math. The actual calculus is pretty simple, but the setup is the part that's going to get us all a little bit hung up. So in order to do that, though, I want to give you kind of the rule of what we're going to be, kind of the process that we're going to, and that'll set up the stage for what we're heading toward. So, wait for that to kick in. The one big rule that we need is what's called the first derivative test. So I want to just and I'm going to tell you that when I write down what the first derivative test says, you're probably in most cases going to say to me, what's the big deal? We've said this probably for 8 weeks now. I just haven't called it the first derivative test. They wait until chapter 4 to really use the term first derivative test. So before I write down what the first derivative test kind of in words says, let me write it kind of in symbols. So the first derivative test is what we use to determine if we have a maximum or a minimum using calculus. Okay? So, if we have a maximum, we have a spot that's a maximum, what we notice is that to the left of that maximum, the first derivative is positive, and to the right of that maximum, the first derivative is negative. We go from increasing to decreasing. That actually is what the first derivative test says, and we'll write it in words. What it actually says is if you have a critical point, so if you have a place where f prime equals 0 or is undefined, and you get this change from f prime being positive to f prime being negative, you have a maximum. Similarly, if we have this critical number, if we have a place where f prime is 0 or undefined, and our derivative goes from negative to positive, then we have a minimum. That's all there is to the first derivative test. Haven't we been kind of saying that? So the first derivative test says if the function has a critical value at x equals c, and remember that means f prime equals 0 or it's undefined, and f prime changes sign at x equals c. In other words, we go from f prime greater than 0, f prime less than 0, or f prime less than 0 followed by f prime greater than 0. Then the function has a what we call local max or, bless you, local min at x equals c. So if a function has a critical value at x equals c, in other words, the derivative is 0 undefined, and the derivative changes sign at x equals c. In other words, we go from positive to negative or negative to positive, then the function has a local max or local min at x equals c. Again, most of you are probably sitting there going, so what? Right? Well, what we're heading into is we're going to be doing some work where we're going to be trying to figure out when a function or where a function has a maximum or a minimum. And so as we're looking for what we will call, I'm going to use the informal term, max-min word problems, and then the fancy term, optimization word problems, the whole goal is going to be to, first of all, write a function. Then what we're going to do is find where f prime is 0 or undefined. And then we're going to test for a max or min. I mean, that's the process. And again, that's the hardest step, is writing the function if it's not given to you. Most of these, not all, but most of these have pretty easy derivatives. Most of them do not have derivatives that require anything more than maybe the chain rule, but most of them are rigged. So it's actually plain old boring polynomial derivatives. I mean, it's the whole point isn't can you take a sophisticated derivative. The whole point is, can you set up the problem and can you take the derivative and set it equal to 0, with the take the derivative, set it equal to 0, and then figuring out where the max and the min being kind of those critical pieces. So, best way to do these is to actually do some examples. And so that's what we're going to do today, is just crank through a bunch of examples. And one thing I need to do is get to my examples, so hang on one second here. I didn't open up my... So, first we'll do one of the, I'm going to call it one of the easier examples, but it's going to be really going to illustrate the process, and it's going to illustrate one of the things that happens quite often in the problems. So, here's the basic boring question. I'm going to flip the page so I don't have to flip the page partway through. What I would like to do is I would like to find two numbers whose product is a maximum and the sum of the first and twice the second is 100. So I'm going to find two numbers whose product is a maximum and the sum of the first and twice the second is 100. First thing you probably should realize is, how do I know this is an optimization problem? How do I know this is a max-min problem? Well, the way I know it's a max-min problem, and this is going to sound dumb, I know, is that I'm finding the maximum. And those are the words you're going to be looking for. Find the maximum, find the largest, find the smallest, find the minimum, find the least, find the most. You know, those are going to be the words that are going to say, oh, this is an optimization problem. So now I need to do the setup of this. And so as I kind of look at this, I know I need two numbers. And I know I need two numbers so that the first plus twice the second is 100. And so I'm going to go back into some of my algebraic skills back from like 8th and 9th grade, where you had to do some of these writing equations and solving equations things. And I'm going to try to use good form. I'm not always the best with good form, but usually I set up and I go, okay, I know I need two numbers. So I'm going to call x the first number and y is the second number. Probably looks familiar from days gone by. Right, so x is the first number, y is the second number. And now, I'm going to sharpen my pencil. Now what I'm going to do is try to get one equation, eventually, one equation with one variable. But many of these questions, many of these problems are set up in a way that what happens is we get two equations. And this is a perfect example of when we get two equations. And the two equations we get have special names. They're called the objective and the constraint. So let's take a couple of minutes and talk about what I mean by objective and constraint. The objective equation is the equation that we will be either maximizing or minimizing, which of course in this case is maximizing. The objective equation is the one we are going to take the derivative of. That's the one we're going to set equal to 0 or figure out where it's undefined. Typically, the objective equation looks like something equals something that has just x's or y's in it. And usually over here is almost what you would almost call the name of the process. And that's not real clear the way I just said it, but I think once we do a couple of examples, you'll see what I mean. The constraint equation is kind of the secondary equation. We use to technically really eliminate one variable in the objective. The constraint equation almost always looks like a number equals something with x and y in it. So it usually looks like 7 equals, 12 equals, 300 equals, 27 equals. And then something with x's and y's or l's and w's or, whatever the variables might be. In many of these, as you look at the problem, you're going to start to see two equations that jump out at you. Anybody want to take a shot at one of the two equations?
X plus 2y.
So Ryan says 100 equals x plus 2y. That's this piece. The sum of the first and twice the second is 100. So Ryan, objective or constraint? That's the constraint. That is not the one we're going to be taking the derivative of. So now what I need is the objective, and that's usually kind of the rest of the wording in the problem. So notice what this now says is we want to find two numbers whose product is a maximum. And it's that product is a maximum that's going to give us the objective equation. And so if I were to write this, and I could ask, but I'll do the first one. If I were to write the objective equation, I'd pick some letter for product, or I'd write out the word product, but I usually just pick my favorite letter, P for product, I suppose. And the product is going to have to be a maximum, but it's this product of the two numbers. And so what I just do is I say, okay, my two numbers are x and y. The P has very little to do with the problem other than it's the name of the objective equation. This, again, is the objective, and this is the one I want to take the derivative of. The beauty of these problems are these are not implicit derivatives. We do not take the derivative of both x and y. What we do is we use the objective equation to get rid of either x or y. And then we take the derivative. So now what we want to do, once we have this objective, is we want to rewrite it so it's P equals something that has only x's, or P is something that has only y's. We want to get rid of either the x or we want to get rid of the y, and we use the constraint. So how do you suppose we do that?
Solve for y in the constraint.
Yeah, we have a choice. We can solve for y in the constraint, or we can actually solve for x in the constraint. I always say do the one that either you're the most comfortable with or is the easiest. So I'm gonna do this both ways. Ryan first said solve for y. Let's solve for y and then we'll go back and solve for x. So we'll kind of split this into two problems and I'll do it twice. So if I solve this for y, I'd have 100 minus x over 2 is equal to y. Or if I divide both of these by 2, I'd have 50 minus 1/2 x is equal to y. Right, x over 2 is the same as 1/2 x. So what I do is I solve the constraint and then I substitute that into the objective. So instead of p equals xy, I'll have p equals x and 50 minus 1/2 x. Now, I could leave it like that. My next step, quite honestly, once I now have p equals and only x's, my next step is to take the derivative. I could leave it like that and use the product rule, but I'm going to recommend to you that if you can multiply it out, then you don't need to use the product rule. And in this case, that's pretty easy. 50x minus 1/2 x squared. Now, I have done absolutely no calculus. So again, what have I done? I found two equations, which is not uncommon. These problems are, a lot of them have two equations. Not all of them, but I found two equations. One is the one I want to take the derivative of. That's the one that says find the maximum of blah, blah, blah. The other one's the constraint, which is usually equal to or is equal to a number, set up as an equation equal to a number, and we use that to get rid of a variable. Classic set of steps. Now, once I have the equation, this right here is all what on the previous page I kind of called step 1, write the equation. Then step 2 is, in this case, find p prime. Which hopefully for all of you is like Yawn City at this point. Right? What's the derivative?
Negative x plus 50.
Oh, Ryan's being slick today. He's saying it's negative x plus 50, or 50 minus x. And now what we do is we do that first derivative test. So we take what we just found, set it equal to 0, or find where it's undefined, but hopefully it's pretty obvious to you right now that that's never undefined. And we solve it. So x equals 50. Now, we're about 80% done. So we're about 80% done. We have two things left to do. One of them students always remember to do, and the other one they frequently forget. The one they always remember to do is, it said find two numbers, so they go back and they find the second number. That's one of the things we need to do. The other thing you need to do for the mean math teacher is you need to show the mean math teacher that what you found is a maximum. We get so excited doing the calculus that we forget to prove it's the maximum. So don't forget, because I hate taking points off for you not showing me it's the maximum. So, typically I do that first. And when I go to do that first, what I do is I make myself my little sign bar. Remember the sign bars we've been making almost to drive you crazy? I make a sign bar, and I just pick my favorite number, less than 50 and greater than 50. And, in this case, if you want, you can pick 49. It's any number less than 50, so I'm going to use x is 0. I'm going to use x is 100. I could pick 49 and 51, it doesn't matter. And remember, where I substitute those is into the derivative. So they go into the derivative. So if I put 0 into my derivative, it's 50. And what's even more important is 50 is positive. And then if I put 100 into the derivative, I get negative. I get negative 50. And so I get a negative. So what's going to happen here is this gives me p prime is 50. In this case, p prime is negative 50. And then I just need to say to myself, I need to say, oh, positive first derivative means increasing. Negative first derivative means decreasing. So therefore, at x equals 50, we do in fact have a maximum. This little chart with this little picture documents to me that you know that it is in fact a maximum. It's important to do this step. And then the last thing I have to do is find the y value. So if x is 50, we said y is 50 minus a half x. So y is 50 minus a half of 50. So y is 25. Ta-da! We're done. Now I'm going to fairly quickly rattle through the solution if I solve the opposite way. Right? I didn't have to solve for y, I could have solved for x. Some of you might have said, well, that's easier. I don't have fractions. Right? X is 100 minus 2y. So p, being x times y, is 100 minus 2y times y, or p is 100y minus 2y squared. So now my function has y's in it. And often students don't like the function with y's in it because you're just so used to x's, you'd much rather just have the y's, gone out of the problem. But it works the same way. Take the derivative. 100 minus 4y. Set the derivative equal to 0. And you get y is 25, which is good because we hope that y gets 25 this direction as well. And if we went back in, right, x is 100 minus 2y. So x is again 50. Good. It checks. And again, we would want to make our sign bar, but this time you put the 25 on. That's what we found when we took the derivative. We pick our favorite numbers before and after. So maybe we pick y is 24 and y is 26, if you want to pick something a little closer. And again, you'll still get a positive and a negative. Still a max. That's good. That's what we want to happen. In essence, that's everything in the section. The only thing that's going to change each time is the work we have to do to write the equation.
Ms. Fairman,
Yes.
to show that effect in max, you just draw the little triangle, I guess you could say, over the 50 or 25.
Exactly, yes. Yeah, some people actually will write me little sentences and that type of thing, but if you draw the sign bar and you put the peak, or when we do a minimum, the valley, the V, that to me says you know what you're doing. And yes, I'm slick on the fact that if you look and go, it's a maximum, so it must go plus to minus. In most cases, in almost every case, if you just make the sign bar the way it's supposed to be, it's probably going to be a true statement. Once in a while, somebody might try to trick you up. Once in a while, you get two numbers, and one of them is the max, and one of them is the min. But yeah, that's all I need for documentation. Excellent question. me show you one of the more classic ones that's out there. And I'm going to do this one by showing a picture. I'm going to actually give you the picture. And then we're going to do one that's very similar to it, but we won't do the picture. Kind of a similar concept. Suppose I have a rectangular pen, and I want to split that into two equal size pens. This is in some ways, this is one of my more favorite questions. You know, when I was a student myself, I thought, oh, this is one of those canned questions. And I will tell you, most of these are canned questions. They're like in every single textbook. The numbers change, but the situation's the same. This is a situation here where, okay, I'm going to build a couple of pens. What I happen to know is this is all fencing. And what I might know is I have 2,000 feet of fence. And what I want to get is the maximum area. Okay? And again, I thought, oh, this is such a canned question. We're probably now pushing 20 years ago. I did this problem in class. The next class, or a couple of classes later, one of my students came up to me. I still can see her now. She came up to me. She was so incredibly excited. She lived on a farm. Her father had just bought fencing. He was actually going to do it up against a river or a barn or a house or something. And she went home and showed her how the calculus we had done she could use to get her father to have the maximum area. Sounds really dumb, but for that particular student, that connection of the math to something that her family did on a more regular basis really had a lot of impact on her and actually made her education seem more valuable to her dad. And her major wasn't math and science, it was business. She was an accounting major. Her actual goal was to get the accounting and business background in order to help the family farm and in order to be able to take over the business aspects of the farm as the family moved kind of through the whole farming process. And so for her to be able to connect that was very powerful. And to be able to do that, in a freshman level class was really pretty cool. So back to the problem. So this is kind of the setup. Sometimes you're given it in words. A rectangular pen is going to be divided into two equally sized pens. Find the maximum area if you have 2,000 feet of fence. Sometimes it's 3 pens. Sometimes it's 4 pens. The process is still the same. What we would typically do, and I'm going to change out of X and Y just because I can. What we would typically do is do one of two things. We would either call this L, and then each of these W's, right? They'll all be the same, and then of course this is another L. Or sometimes students will say to me, could I call this L or X and Y? Could this be an L? 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 And then all those, you certainly can. The equation you set up will just be slightly different. But I'm going to label every piece of fencing with a letter of the alphabet. An appropriate letter of the alphabet. Again, and almost the way I wrote it, you could almost see those two equations jumping out at you. We want to find the maximum area, so that's going to be our objective equation. And the fact that I gave you 2,000 feet of fence, that's what's going to give rise to the constraint. And we just need the equations that go with it. Area, the way I set it up, right? It's a rectangle. Area of a rectangle is base times height. So in this case, area is just length times width. Now, if we had, and I'm just going to sneak this at the bottom of the page, if you'd said L, 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 W, 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 Then really what you have is a situation where you either have two rectangles that you add together, or the base is 2L and the height is W. Either way, you're going to get this 2L. It's not, the actual answer you get will end up being the same. You'll end up getting the same area. The formula is just going to use a little different getting you there. But typically this is what you'll see books do. They'll call the whole length L and the entire width W.
Is the objective going to always have just two variables in it?
Yes, the objective, well, the way we will do the problems in Calc 1, the objective will have just two variables. And that's what Ryan asked, is will the objective always have this only two variables when we're doing these two? Yes. For those of you who are going on to science and engineering careers where you might go to Calc 3, in Calc 3, you go into this more of a multivariable situation, and there's some additional ways you would solve the problem. You have some additional skills to do. But in Calc 1, we need to be able to get everybody back to one variable, and so that's the way these get set up, yeah. And then we have 2,000 feet of fence, so make sure you count every piece of fence that you have. And so what's going to happen is you're going to have two L's and three W's. That's what's going to give you the 2,000 feet. Now the process we just did, we repeat all over again. Right, we repeat the process. We solve this for one of the two variables. So I'm going to solve, I think, for L. The beauty of L and W is you don't get into this X and Y thing, which sometimes students always want to make sure their equation has X's in it. And that sometimes is a harder equation. So I'm going to solve for L, and if I do that, that's going to tell me 2L is 2,000 minus 3W. So L, when I divide by 2, is going to be 1,000 minus 3 halves W. Just like we did before, we take that and we stuff it back into the objective. So A equals 1,000 minus 3 halves W times W, or 1,000 W minus 3 halves W squared. And yes, I know the algebra and the calculus are kind of redundant. They're not all the same. Don't go, oh, I've got those, so I'm really good on this section. We're going to twist it up a little bit on you. But to be able to see the process and do the same thing twice, you kind of see how the process works. Take the derivative, 1,000 minus 3W. Set the derivative equal to 0. And so we get W is 1,000 over 3. In other words, approximately 333.3 feet for the width. Go back and get the length. The length is 1,000 minus 3 halves the width. I'm going to go back. I'm not going to use the decimal for the second because the math comes out nicely if I don't use the decimal. I get that L is 500 feet. This is a 10-point question. We now have 8 of the points. We get the other 2 by showing it is a maximum. Let's see, the item we found was the W. That's what we found from the derivative. So maybe I'll pick W is 0. Maybe I'll pick W is 400. I like nice round numbers. They're easier to do math with. Put 0 into the derivative. Here's my derivative. Right, put A prime at 0. When I do A prime at 0, that gives me 1,000. Again, I don't really care that it's 1,000. I care that it's positive. Good sign. And then I do the derivative at 400. 3 times 400 is 1,200. 1,000 minus 1,200. Negative 200 again. I don't care that it's negative 200. I care that it's negative. So right there at the 333.3, based upon the first derivative test, I know that I have a maximum. Now, if this question said, find the max area, sometimes it says find the dimensions, sometimes it says find the maximum area. Make sure you answer the question they asked. So if this had said find the maximum area, I would have one more step I would need to do. I would need to actually compute the area. I have lots of ways I could do this. I probably would just do length times width. So that's 1,000 over 3 times 500. That's going to get me 5 with 5 zeros. Divided by 3 square feet. And I could pull my calculator out, but I'm being a little lazy. So let's stop here for a second. How are we feeling about the process? Does the process kind of make sense? What do you want me to do? Move it up? Down? Over? Can you widen it? Does that do what you need me to do? These are not, what's funny is these are not really easy questions. Some students find them very easy because they've had a really good experience in the past modeling equations, writing these kinds of equations, and so it feels pretty natural to them. Some students really struggle with them. Doesn't seem to be a whole lot in the middle. The nice part is, usually in testing situations here, we tend to give a lot of these really routine questions. It's not unusual for us to give this question right here. I want to show you another one before we go that doesn't have the two equations. You want to see one that doesn't have two equations?
Why not?
Why not? Sure, I agree. So and this one I'm going to confess I'm making up out of my head, so I apologize. The numbers could come out to be a little squirrely. So here's the situation. Let me put this back on me for a second. So here's the situation. Have you ever engaged in this, and I actually remember doing it, although not exactly the way that I'm going to talk about it. I actually did it in 8th grade shop class, where you take a piece of metal or you take a piece of paper that's rectangular and you cut out the 4 corners and you fold the corners up to make a box. Now in shop class or something, you usually do it so that there's little tabs so that you can weld or whatever it is that you might solder, whatever you might need to do. Here we're not going to do that. So here's the situation that we're going to have. What we're going to have is we're going to have our piece of paper that starts this way. And what we're going to do is we're going to cut out four equally sized squares. So they're all going to be the same squares, which is going to give us, and I never can draw this quite right, so forgive me. I have a horrible time with drawing the symmetry. It's going to give us something that looks kind of like that. And then on those 4 dotted lines, we're going to fold up and make a box, tape the pieces together. So what we're going to know is we're going to know the dimensions of the original box. So what I might know, not box, but the original paper, what I might know is this might be, say, 20 inches. And the original paper might be 10 inches wide. And what I want, I'm on a maximum kick today, is I want the maximum volume. Okay? This one is only going to be one equation. It's a little bit of a different setup. Now, I do know I want the maximum volume, and this is when we're going to go, now wait a minute, volume is like length times width times height. Now you got three letters, lady, and you told me there are only two. Well, you'll watch what happens. We'll actually give rise to really only using one by the time we're done here. So the setup here is I don't know how big these squares are. So I'm going to call the dimensions. Remember, I said that they're squares, and they're all the same size. So I'm going to call them all x by x. Which means if I translate all those little x's over to the second picture I drew, and I transfer those measurements, that's what I have. Now, in order to get the length, the width, and the height, what hopefully you realize is this dotted rectangle I drew, that's the length and the width. That if I can figure out how long those dotted sides are, that's going to give me the length and the width. So let's check. If I call this the length, if the 20 direction, if this right here is the length direction, how big is that dotted length?
20 minus 2x.
20 minus 2x. If you could see Ryan right now, he looks incredibly bored. I'm keeping him awake this morning. He told me he was tired. I'm tired too. Oh, it's hard that first week or so back from vacation. So yeah, it's 20 minus 2x. The whole piece is 20. I actually take out this x and this x, so I get 20 minus 2x. And then the width dimension is very similarly going to be 10 minus 2x. There's my length, there's my width. How tall is the box? X. Very good. We don't have two equations, but we are actually kind of using that 20 and 10 in almost a constraint type of behavior. That's what I want to take the derivative of. Again, you might look and go, oh my goodness, do I need to use the product rule? What do I do? I'm going to really tell you that on a problem like this, the cleanest thing to do is just multiply out all that stuff. So FOIL these two together, so it's going to give me 200 minus 40x minus 20x plus 4x squared, all multiplied by x, which is going to give me 200x minus 60x squared plus 4x cubed. I will warn you, I've just made this problem up, and so I likely have made up a problem that's ugly at after the next step. But we can kind of talk through what we would do, and I would tell you if I ever put this on a test, I don't make it ugly. But you have to pick the right combination of numbers. This is my volume. I now have the equation. I've done no calculus. Now it's time to do the calculus. Take the derivative, 200 minus 120x plus 12x squared. My math okay today? And this, I now set equal to 0. And this is why I've just made this ugly. Is this quadratic? I might need to use a quadratic formula on. Usually I try to rig them so I don't need to. I'm probably not going to do all the work out here, but we'll kind of talk through it. See, all of these are divisible by 4, so I actually would have 4 and then 3x squared minus 30x plus 50 equals 0. And then I would solve this. Because this is quadratic, you actually get two answers. One of them is the answer and the other one is not. Usually what happens on these problems is you get two solutions. What happens is technically one of them gives you the max and the other gives you the min. Usually the one that gives you the min makes no sense in the problem. Usually that one makes absolutely no sense in the problem. And I may be able to, I got a minute or so. I got a quadratic equation solver. I'm going to cheat. 3 minus 30 and 50. No, I cheated. So I'm going to get about 7.9 and 2.1. The 7.9 one makes no sense. And if you go, well, what do you mean? If I cut 7.9 inches off of here and 7.9 inches off of here, I only had 10 inches. It's not physically possible to even do it. And so in these problems, usually one of them just literally makes no sense. You could not do that to that piece of cardboard or paper. And then this one, if you actually did it, in your V prime, you would find that situation again. So there's one where we don't really have that. There's some really funky algebra that occurs, okay? Some really funky setups. What I'm going to do is on Monday when we get back together, I'm going to do some of the other funkier ones. So what I really want you to kind of do is take a look at these that I've talked about here. Make sure you are comfortable with the process. Because what we'll do on Monday is I'll do some of the funkier setups. Does that make sense to you? You're guaranteed to have one or two of these on the final exam. The question I just did with the box is almost, I've got a minute or so, is almost identical to the one that was on the final exam last year. I have not seen this year's final exam. The one that we had last year, the box was just different. And I won't be able to get this right, but it was something like, it was a pizza box, and it had like, so you're going to have all these folds, and you like started with like 40 inches here and 20 inches here, and you had to be able to think now to yourself, how big were the things? And so you had, so instead of being like 40 minus 2x, it ended up being like 40 minus 4x and 20 minus 2x, and then it still became the same kind of volume. But the picture kind of freaked people out a little bit because they were okay with this one, but this one here, that they just looked at and like freaked. But it was a very similar type of question that we've used in the past. That one and the first one I do next time are the two that we typically see on the final exam. Let's quit here and let's have a nice weekend. How's that sound? I'm going to go home and recuperate from my week and maybe have my own personal accreditation party. Have a great one, everybody. Bye now. Have fun in English. I must really be winding down too.
Yeah, we're on our final paper. If we get done with that, we don't have to go anymore, so.
Oh, there's an incentive.